thank you everyone for coming. Sorry for the delay. So let's just crack on. So I'm talking today about how we recycle plastics, and yes, we can. So a little bit about me to start with. I talked here last year, but in case anyone didn't come to that, I'm from around here. I went to school in Stourbridge and in Birmingham, and then I went to university at Cardiff and for a year in University of Ontario. I went to Glasgow to do my PhD. Up until very, very recently, when I last did the talk, I was just about to finish my PhD, and it was, if anyone was there, it was all about colour changing windows. So this is quite a different sort of topic. What I'm doing now is something called a knowledge transfer partnership, and this is between a company who want to solve a problem and a university who have the knowledge to solve that problem, and I'm meant to be a sort of gap in between to sort of apply the science to real life. Because of this, I work in two very, very different environments day to day. So I work at the Carbon Neutral Labs of Nottingham. This is the building on the left, which is a wooden chemistry department. And if anyone remembers it being in the news, it burnt down before it even opened. But now it's been rebuilt and it's functioning fully. It's exactly what you'd expect a chemistry department to be. It's full of high-tech labs and it's very new and shiny. Whereas Trelleborg, which is the company that I work with, they are basically a production site. So it's a really big shop floor. They don't do a great amount of science in terms of the lab, but they produce a lot of material and they send it out, and they make a big variety of polyurethane products. So I sort of manage my time between the two. And the project's all about sustainability. So just to talk a little bit about sustainability first, the UN have given 17 sustainability goals, and I've got a little video which hopefully will play, just to sort of go over a couple of those. To highlight that there's so many different aspects of what people define as sustainable, and the project I'm working on now kind of encompasses a few different ones of these goals. So particularly thinking about life on sea, life on the land, industrial development, and sustainable use and consumption. Something else that is being touched on, just because I work in a chemistry department, is the field of green chemistry, which is only very slightly younger than me. It was first sort of put together by Paul Nassas and John Warner somewhere between 1995 and 1998. 1998 is when they published, and they set out 12 criteria. You don't have to read it all. It's very detailed, but there's 12 criteria by which they thought this is what sustainable green chemistry means to us. And since then, the field has developed and developed. They're still working together. They're going to write a new book about the field very soon. So my project is sort of focusing on mainly these two principles, which is prevention of waste and renewable feedstock. And it's all about recycling plastics, as I said at the start. So plastics have been around for over 100 years, and there's so many different types of plastic, and they're in so many different products, and they've been used for different types of things for this entire time it's been around. So whether that's fashion, whether that's music, affordable furniture, or more disposable products that we've sort of come to know as commonplace. Plastics, I'm sure everyone knows, have only gone up and up and up in production, especially over the last sort of 20 years or so. But the amount that is recycled has not massively increased, and the final numbers aren't particularly good. So about 9% of plastic is recycled, and about 12% is just burned, and the rest of it tends to end up in landfill. And it's a problem everyone knows. It's the subject of so many documentaries, including Blue Planet, that these things end up in the oceans. They end up damaging. They damage life both on land and sea. You know, the plastic bags get tangled up in different types of sea life, and those you know, the cans for beers and cokes end up like choking different types of turtles. It's a real problem that we do need to look hard at. But we didn't really realize this was a huge problem until it was a little bit of a massive problem. So this led to a bit of a sudden change in direction. So until a certain point, polymer chemists were basically told, we want this as strong as possible, as durable as possible. We want it to be the best of the best of the best. And then sort of when we start to realize that this was having impacts on our planet, the narrative sort of changed to, we want the best of the best and the toughest of the toughest, but when we want it to be end of use, we want to be able to snap our fingers and then suddenly we're able to melt it down, recycle it, and it's not as durable anymore, which was a real challenge for the scientific community to sort of look at, and we're still looking at it now. So that work is still nowhere near finished. So I work with polyurethane, and I'll come on to a bit more about that in a second. But polyurethane is a particularly strong type of plastic. It's not the sort of plastic that would be used in just disposable plastic bottles. It tends to be used for quite durable applications. It's because it has a lot of strength and a lot of resistance to lots of different things. And the variety of products it's used in are really quite large as well. So the main thing that Trelleborg, the site that I work at, produces is mainly sort of absorbent, vibration absorbent materials. So they make sort of panels and rail covers. So when the trams in Nottingham, they make the covers for the rail for the tram, so that when it goes through and it vibrates, you don't get as much noise. But it's also used in lots of different things. The main use of polyurethane foam is in cushions. So most furniture that people own is full of polyurethane, just in a slightly different form. It can also take on quite a rubber-like form as well, like a squeegee blade. And that's the sort of type of polyurethane that the site I work at make. So you don't have to worry too much about the chemical makeup, but it's made up of three parts, two main parts, which is an alcohol and something we call an isocyanate. And these two things react together, and they just keep on reacting and reacting together in a big long chain, and that's what makes a polymer. So they'll just keep going and forming these really long chains, and sometimes we also put little extra bonds and extra links between those polymer chains, and that adds a little bit of stability. So we have those two things that make up the chain, also known as the backbone, and we have our bridges. Now, it's quite easy to make a really big variety of types of polyurethane just by varying the ratios of these three components. So we have a three-part mixture on site, and we change that ratio, and by that we get a huge range of hardnesses, of toughnesses, and these can be color-coded and easily shipped out. It mainly affects the flexibility of the polyurethane. So there's loads of polyurethane everywhere. tons and tons and tons of it are made every year, but about 50% of it ends up in landfill. This is the kind of situation we have right now on the left, where things are just going to landfill. And on the right, we have a fully circular economy, ideally, where everything's made from natural products and we can recycle it and use it again and again and again, and nothing gets thrown away. In the middle is sort of roughly where we are now, and it's a step in the right direction. So we're getting there by increments, but Rome wasn't built in a day, and it's all about getting some further longevity and reuse out of products to help us get towards that point. So the reason that so much isocyanate ends up in landfill is because of a difference between the makeup of different polymers. Polymers can either be what we call thermosetting or thermoplastic, and thermosetting plastics have those bridges, those bonds in between that I talked about, whereas thermoplastics don't. They're just straight chains. And when we come to recycle these, if we heat both of them up, a thermoplastic, because it doesn't have those links and those strong bonds, will just sort of melt. It will be able to be poured into a new mold and remade into something new. Whereas thermosets tend to just burn and give off a lot of nasty chemicals. And for that reason, they're not very recyclable at all. And it's because of those strong bridges in between the polymers. Now, the reason that this is a problem, as well as an advantage, it's an advantage because it makes these great, strong, durable polymers, and they are used in things like conveyor belts and moldings and rollers, and but a lot of polyurethane is thermoset. But there's different ways that we can come across recycling. So the thermoplastics, which don't have these strong bonds, they're typically sort of ground up at the recycling plant and poured into, you made something like an extruder, sorry. And that is a bit like a big Play-Doh machine. It all gets poured in, it melts, and then a screw sort of turns and pushes out that molten plastic through a die, and we get these sort of uniform rods in different shapes. And that's typically how most thermoplastic material is recycled. The problem with that is when we keep heating up and melting things, their properties get worse and worse over time. It's a bit like photocopying a photocopy of a photocopy. There's only so many times we can do it before it's not really usable in the real world anymore. So thermosets typically are chemically recycled, and that is basically trying to get back those individual puzzle pieces, that isocyanate and that alcohol. We're trying to get that back from a solid plastic and hopefully reuse that again in a new product. But it's quite a nasty chemical process, the most common being something called pyrolysis. And that's basically getting your ground up plastic and heating it without oxygen, usually with a catalyst, and what you get out is a bit of a horrible mix of different things. It's a bit like getting a pot of green paint at the end and then trying to extract yellow and blue from it. It takes a long, arduous separation process. It takes a lot of time and energy, and by the time you've finished, is it using more energy and producing more greenhouse gases than it would have been just to throw the plastic away, which is a big problem with chemical recycling. It usually has like quite toxic byproducts as well. Other people, in fact, someone who's in the chat, a former speaker, Ben, is working on, I think, bacteria as another way to do this sort of chemical recycling, but in a more environmentally friendly and less toxic way. So it's something that a lot of people are working on right now. So as I was saying, a lot of the polyurethane market is thermoset. About 76% of it is thermoset. So 76% is a difficult thing to recycle. And tons and tons of it are made every single year. So the approach that my project is trying to use is keeping that strength and keeping that durability, but also adding the flexibility to recycle. And hopefully from these pictures, you can kind of see where I'm going with this analogy. What happens when you have a big bridge, but you want a boat to go through the water? You get something like London Bridge. So no one would have any problem walking across London Bridge after it's gone up and closed again. It still has that stability, but it also has the flexibility to open and close. What we want is to make those little bridges and those bonds between our polymer strands into essentially little London bridges. We want them to open and close when we want. Once they open, it will turn into a thermoplastic. It'll be able to melt, to be reformed. And then when we want, we can close the bridge again and, in theory, get back to that strong, durable plastic once more. So that's the theory behind what I'm working on now. So in academia, we call this a self-healing polymer. There's a few different categories of this, but in general, the idea is that once it's cut or there's a fault within it, it will be able to heal. And it won't heal forever. The performance will go down over time, but it will essentially be used a lot longer. So it was a really hot topic. You can see the number of publications just went up and up and up and up in recent years. But we're not seeing them in everyday products. No one sees a self-healing polymer in the supermarket. So why is that? So there's a few methods of healability. One of the most common is something called encapsulation. And that's essentially like having, I've put a little picture of bubble tea here, which I think is the best way to describe it. There's little capsules, little fragile capsules of healing serum, essentially, made out of a catalyst through your polymer. So when you break it, these little bubbles pop. Sometimes they're in rods as well, but something will break. It will release that healing agent, and then everything will reform and heal your polymer, and it will start to sort of bleed out, as you can see in this picture here. It will start to bleed out of the polymer, and there's been a lot of reports of this, and it tends to heal pretty well. But there's a few problems here. So what happens when you use up all of these bubbles of healing material? There's going to be a limit eventually. Also, if you were to cut the exact same spot twice, which is likely to happen if something was to break during use, it's probably going to break in the same spot again. It's not going to be as effective the second time round because you've already used up all of the capsules around that spot. So this is a bit of a major drawback for this sort of field. Also because catalysts usually use precious metals, they tend to be quite expensive, and there's a finite source of them, so it isn't very sustainable to put this in just to make your polymer a little bit more recyclable. Another method, which is the one we are using, would be to take that bond, that cross-linker, or another link somewhere else in the polymer chain, and instead of making it a solid bond, we would make it into something that is of two halves. And those two halves, when we wanted to, could be broken apart and put back together on demand. This is something that we call a covalent adaptive network, or a C.A.N. So that's what the title of the talk was called, Yes, We Can. So it's a covalent network basically means a covalent bond is a strong permanent bond, but it's adaptable, so we can break it apart when we want. This is a really promising attempt to add recyclability to polymers. So there's a few different fields, sort of different approaches to this field. One of them is light switching materials. And these materials, when you apply a certain wavelength of light to them, will form new bonds or break bonds. These tend to be in the sort of violet end of the visible spectrum or beyond, or into the ultraviolet. However, the problem with this is that if that wavelength was just about in the sunlight and it is touching onto the visible spectrum, if that wavelength hits the plastic when you don't want it to, you could essentially just start melting your plastic, not like when it's in use, and that's not what we want at all. We want to keep that stability. So we want something that's more like a light switch. We want something a bit more on demand and a bit more controllable. So this is what I am working on. So we utilize an area of chemistry called Diels-Alder. It's named after the people who first discovered it just under 100 years ago. And it was given the Nobel Prize in 1950. It's a very well-known area of chemistry, it's very established. It's taught at undergrad and even high school level. So it's been around for years. And the way it works is that two things come together and make a ring. And they can do this because the bonds, particularly those double lines, are double bonds, extra strong bonds, they have extra electrons. And these electrons can move around and form new bonds to create that circle. Luckily for us, it is reversible. So when we apply heat, those electrons can move back and recreate the original materials that they started as. So when we heat something up, it breaks apart. And when we cool it down, it goes back to that cyclic structure, which could be that sort of London Bridge motif that we were looking for. So that's the approach that I am doing in my work at the moment. This sort of approach has been reported, but it's typically in the polymer chain itself. So when people apply heat, it breaks a long chain into just smaller bits and makes it a bit easier to recycle. But the approach we want to use is to really focus on that cross-linker. Leave the polymer chain as it is and just focus on that one part of the three-part system. The idea behind this is that the more we focus on how easy it is to implement, the better it will be for industry to pick up. That's the whole point of having this sort of collaboration with industry. Because, as I said at the start, all they do is vary the ratio of these three things to make a big range of different durabilities and hardnesses. If we could replace one part of a three-part system, we could potentially affect quite a large range of products. So that's the thinking behind the work right now. So at the moment, we're just doing theoretical studies. The next step is to put it into a polymer system, which is something we hope to do in the next couple of months. But I'll try and quickly explain the sort of theoretical stuff behind what we've been doing as easily as I can. So we've been following the opening and closing of this linker with something called NMR, which stands for nuclear magnetic resonance spectroscopy. And this is quite similar to an MRI scanner, really. It uses a big magnet. And we put in those two halves and into a tube, and we basically watch it as it comes together and breaks apart. And very, very, very quickly, how this roughly works is that different atoms in the sample have something that we call a spin. And all that really means, it's a bit like a magnet. You have a positive or a negative end of a magnet. Spins can be one way or the other. It's very similar to that. When we apply an external magnetic field in the way that you do in an MRI scanner, all of these atoms sort of align themselves either with or against the field. So you go from this completely random configuration to something that's a bit more 50-50. And then when we take that away, everything relaxes back down to randomness again. And what we get is energy given off during that process, and we basically measure that energy. And that's what we've been doing. And it's very, very distinctive for different kinds of, or different parts of the molecule you're looking at. So using that, we've been able to study the linker that we've made, break apart at high temperature and reform again. So here you can see this is some of the data that we've collected. So it basically breaks up about 70% in an hour at 100 degrees. And then reforming it is a little bit more tricky because it involves a bit of trial and error. So we've tried different temperatures and different lengths of time. And we found that this temperature, which is marked as a green X, after this point, we start to see a much better yield. And we also see that it takes about 8 hours to happen. So from these sort of provision experiments, which are all in solution, we're hoping that we found the perfect conditions to then apply that to a polymer system, which is the next steps of the project. But we've proved that this will essentially break and come back together, which is really, really promising. Another part of this is asking where is the demand for these sorts of things. So we've set out a few criteria that we think is the best way to get the ball rolling. We want something that has a short lifespan because we want something that will be sent back to be recycled. We don't want something that's going to sit like the rail that I was talking about earlier. That's going to sit in the ground for quite a long time before it needs to be recycled. So we want something that's shorter time span than that. Ideally public facing, because they'll be more likely to engage with us. A cheap product they won't mind sending back, and nothing that's in too heavy a chemical environment, because that will just add a little bit of complication. And the area we've chosen is recycling centres. So they use something like this picture on the left. This is a mining mat or a screening mat, and it's used as a big sieve, essentially, to separate the different sizes of things. And they're used in recycling centres for about 6 to 12 months at a time. They have quite a short turnaround, and the rougher the material that goes through them, obviously, the quicker they fall apart. So we have been talking to recycling centres who might be interested, and hoping to do a trial with the material soon, just to sort of see what the feedback is and to get some real world data, which is really exciting. So the sort of last thing I wanted to talk about is about where the demand actually is. And this is a sort of just sort of showing where the sort of process is. So chemicals are made at a big chemical plant, mainly using fossil fuels. Those chemicals get sent to somewhere like I work, where they do the mixing and casting, and they make a product. And then that product is sent to somewhere else. This is an example of plastic bottles. So it'll get sent somewhere, a factory that actually makes the product that goes into the packaging and get filled. And from there, usually there's a distribution company somewhere in the middle as well. And from there, it gets distributed again to the supermarket. And at that point is where the general public will start to use it. Now, the problem is when you talk about sustainability and people trying to make more sustainable choices and to recycle, your reach is only as far as perhaps a supermarket. And when you do start to recycle, and the council comes and picks it up, and then it goes to a recycling centre and gets sorted and washed, and then usually sent to a different processing plant, which makes it into new material that then gets sent back to the place that fills it up and then goes back to the supermarket. We're creating a second loop, basically. So this could look like a circular economy, but we've got the second loop going on, and that's what's using the fossil fuels and the greenhouse gases. So these two parts of the chain don't really get affected by the choices that we make at the far end. These parts of the chain only really get affected by government policy. And that's why I think it's always good to make sustainable choices and to recycle, but it's also good to keep an eye on things like government policy, because that's where we're going to see the real change in this sort of industry. We hope that it comes soon, and projects like the one I'm working on will hopefully help bring that about as well, and to get ahead of those policy changes, which we're pretty sure are coming. So finally, a little bit of future work. As I was saying, the next step is to start putting it into polymers and see how it works, and to start getting it out there in the real world, hopefully. On a side note, a few things that could be looked at as well are these areas of green chemistry, and they're all about how efficient the synthesis is. So how efficient is it to make these materials? Could they be made in a safer way? Could they be made more efficiently? Things like that. So that's the sort of work that we're doing at the university, just to see, to make it in the best possible way, at the same time as doing all these material tests over at the company. So lastly, I'd like to thank everyone for listening. Sorry about the technical issues and everything being online and coughing all the way through it. I hope you enjoyed the talk. Just thanks to everyone for coming, and online and in person, and thanks to all the collaborators that I'm working with right now. And thank you all for listening.